So, in the last classes, we talked about YOLO version 1, or it was basically YOLO. So, what exactly was the structure of the whole YOLO thing? We talked about how it uses GoogleNet, then it adds 5 more convolution layers, and finally, once you have all the features extracted, you reshape it to form a 7 cross 7 cross 30 kind of a structure. And we actually understood why there is this 7 cross 7 cross 30 architecture. We understood in depth how you have an image and it has been divided into grids of 7 cross 7, and then each grid is representative of this 7 cross 7, and each grid value gives out 30 different values. We talked about how these 30 values have been formed itself. All right, so those things we know. And then what we talked about is we talked about non-max suppression. If you remember, what was exactly non-max suppression algorithm? So in non-max suppression algorithm, basically the thing was, when you have the values, you compare the maximum value to all the other current values, see if the IOU is greater than the threshold IOU. So in this case it was 0.5, and then if it is greater, that means chances are that both boxes represent the same object. Hence the one that has a lower value, a lower IOU will be removed, lower confidence level, sorry. And in that way you have a lot of zeros and you have a lot of values. Once those come out, the only thing that will be left is basically you will have to divide it based on the values that you have gotten, whether that bounding box should form a square or not, or a bounding box or not, right? So that was the final whole thing about non-max suppression. One thing I forgot to mention was the loss in YOLO. I don't know how and when this happened, but yeah, I remember later on, okay, there is also something of loss, and we did not cover that. So the loss is not that great. I mean, it is a very simple thing. It is sum of squared errors. Okay, so that is basically what the loss is. We will talk about this in details. Let us understand each and every term. So it is basically sum of squared losses. Like you can see here, all of these are squared values. So sum of squared errors is basically the loss that we have. So let us talk about each value, starting from the first one. By the way, these are parameters, these lambda things, these are parameters. They help giving weight to the loss function, so that suppose one part needs more weightage compared to the other, so in that case we have a lambda, so that it provides more weightage. So that is why we have the lambda, and lambda is a trainable parameter here. So let us talk about the first term. This is my first term. So what is the first term? Basically xi minus xi bar whole square plus yi minus yi hat whole square. If you remember this sounds kind of familiar, does it not? So this is basically your mean square error loss without doing the root mean square. All right, so this is the square error loss. So whenever you have these anchor boxes that come, you have the center. So how much should the center be moved? So that loss, if the center has been moved, the loss will be higher, else it will be lower. So that is why the center value. By the way, this term, this I obj, this basically represents if there is an object. So that means this whole thing will only work if you have an object in that particular grid. All right, if there is actually an object, and then suppose this is my grid, and I have made this bounding box. All right, so the center, so if it has an object, only then will this be activated, else this will not be activated, because we do not want to penalize things that make no sense. All right, first that is done. The next thing is basically this one. So this is again plus under root hi minus under root hi hat whole square. So what this is basically, see, you have these anchor boxes, you get the center, you subtract the center values. Now you also have the width and height here. So if suppose your ground truth is somewhere here, this is your ground truth, this is the one that you predicted. So in that case, the difference in width, the difference in height, that needs to be calculated. Now here is the thing, the reason why this width and height is under root, so that they do not actually become very big values. If your height and width becomes very big values, if they become, so in that case what will happen is the whole model will work on making sure that your height and width of the boxes are similar, but they will not make sure if your centers are similar, or if the confidence values are similar, or if the probability is similar. So hence this under root makes sure that they always stay in limit and do not cross it a lot, right? So that is why this thing. Next what we have is ci hat whole square. So this ci hat whole square is, if you remember, ci minus ci hat whole square. So this is basically your probability of object, or objectness score. This is also known as objectness score. So probability that there is an object, this is the confidence value for that, and this is the actual value. So actual value can be more like, let's suppose, yeah, if the object is present in that grid box, the actual value will be yes 1, or, and then it will give you my probability, like I am 0.3% sure. So then the difference here and square of that will give me the next value, the third value here. This only works if there is actually an object. If you think about it, you have 49 grids, right? And out of these 49 grids, only 9 grids might have object. I mean, not all grids are gonna have objects. Most grids are not gonna have objects. So that is why we need to make sure that we do not penalize or do anything where this part does not work. And then you have this value here. This is 1, but here instead of object you have NOOBJ. That means no object. Now this is basically so that, see, all this time we are just making sure that there is an object and hence it will be activated, right? But there might be chance that it has been activated, it has given me a very high probability, but even then we do not have any object. So hence we need to take that also into account and add this value, hence this value, alright? And here also you have lambda, so you can control the parameter value that you want here. And final here is probability of IC minus PIC mean. So this whole square, I suppose, yeah. So what this means is basically this is probability that it belongs to a particular class, See, like I talked about, there are two important things here. If you remember, when talking about probabilities, we had two different probabilities. So we had one probability of there being an object, probability of object, and then we had probability of class if there is an object. So if the grid has an object, in that case what is the probability that it belongs to particular class? So what here is basically, see, let's say I have grid, and in that grid I have a dog. So the actual probability is only for dog class to be 1 and all the other classes will be 0. So all the other 19 classes will be 0. And here they will give values, I mean the values are going to get, but if you are just starting, so this is not going to be very high. Let's suppose this gives me, I don't know, 0.2 as the dog class, and the rest it's giving me 0.1, 0.3. So that value also needs to be calculated, that you are getting some loss. The only way where you will not be getting a loss here is, so this term will be 0, will be if your probabilities that are given out by the model for dog is 1 and the rest all is 0. So in that case, all the zeros subtracted with zeros will become zeros, but at the same time this dog class 1 minus 1 will also become 0. Hence this whole term will become 0 and your loss will get reduced. Now are you getting this term value? So C belongs to all the classes here. Since YOLO V1 was trained on 20 classes, so here you have the values that will be subtracted for 20 such classes. So there are two different probabilities you need to consider here. This as the objectness code or confidence that there is an object, and this the probability of that particular class existing in that grid if there is an object. Alright, and then these are the subtracted values obviously. So this is basically the whole thing about YOLO loss. So if you can see here, there are nothing in any losses like logistic regression or some other thing. This is basically squared error losses, and they have all been summed up, right? So sum of squared errors, like you can see. So this is the whole thing about YOLO V1. Now we have completed it. Okay, so now what we will be talking about is YOLO V2. So this is the version 2 of YOLO. A lot of changes happened. First, let us talk about what were the cons with YOLO V1. So the very first con was basically it just detects 49 objects. Since you have 49 such grids, so it is going to detect objects there. So it just detects in that case 49 objects, right? And secondly, it had high localization error. What high localization error basically means is even though you get the values right, even though you get the object and everything, but still then the bounding box values are not very correct. So these were some of the problems with YOLO V1. Hence we had the concept of YOLO V2. Now let us talk about what happened in YOLO V2, what were the advances and everything. So in YOLO V2, first of all, they added batch normalization. Like I've been saying, batch normalization is very important, because if you remember when we talked about the analogy and we talked about how a white dog can have a different distribution but from the black dog, but we want both of them to be tested and labeled as dogs. In that case, if we have that problem, it could be something. Hence what we do is normalize them so that both have the same values, or they belong to the same distribution basically. Next, instead of doing 2 bounding box per grid, this changed to k bounding box per grid. So this k is basically decided by us what we want as the value and everything, but yeah, it was changed to k bounding boxes. And what this helped is so that now we can be able to detect more objects. One thing that you need to know is, see, even when you might have thought about this, if you remember when we were talking about YOLO V1, right, we talked that there are 49 grid cells, but if you remember, for each grid cell we had 2 bounding boxes, so it should be 98 grid cells, right? But no, each grid cell was responsible for only finding out one object, right? And hence because it was only responsible for finding out one object, so at most we can detect 49 objects from there, even though there are 2 bounding boxes. Hence this concept was changed, and what they did was, we have k bounding boxes, and each bounding box can be responsible, or each grid can be responsible for more than one object. So that was basically the whole thing about this second part, which made it better actually. And some other, now these are some basic reforms that they did, right? By the way, this k here, this k is equal to 5 when they trained in YOLO V2, and how they got this value is kind of interesting. So what they did is, okay, so the k value was basically found out using k-means clustering. So what they did is, they got the data set, and they found all the different values, all the different dimensions of the bounding boxes, and they did a clustering algorithm, and they found out, okay, so the number of number of bounding boxes, number of size of bounding boxes, or number of bounding boxes that we require are 5, one from each particular group. So this whole thing k was decided using k-means clustering. All right, so this was one thing. Next, what they did, now these were some of the minor changes, okay, these were some of the very minor changes, but they also did some very big changes. Like, for starters, they removed GoogleNet now. So Inception V1 or GoogleNet that was being used was removed, and now what they introduced was Darknet. So you had Darknet 19. which signifies that it had 19 layers, all right. And the reason why they introduced this, because they thought it is their data set and their values, so they should know and they should have the power to control it, hence they introduced darknet. And also there are a few other features of darknet, we will talk about it, but yeah. So darknet is basically, if you can see, convolutions and residual layers. So it removed the idea of inception and it added the idea of residual to the whole thing. Hence you have 19 layers, and you have these convolution values like you can see. So this was basically the whole structure of darknet. So the thing basically is, earlier when I learned about darknet, I thought darknet was a framework on which it was built, but no, darknet is actually the architecture of the basic main architecture of YOLO, and from that main architecture it removed Google Net and added darknet. This helped improve the accuracy actually, all right. So the second was that. So now darknet, what it basically has is 19 convolution layers and 5 max pooling layers. So these are two important things. Okay, now what other thing is that for classification they trained on ImageNet dataset on 224 cross 224 size of the images for 160 epochs, and then after that they trained this whole classification again for 488 cross 488 size input size. Now this was only trained for 10 epochs. Now the reason why this is done is basically this helps improve the accuracy, kind of gives you an idea about an image pyramid. Image pyramid is basically, you have the object here, right? And if that object increases in size, let's say now this is your object, okay, so this is a small object, this is the bigger object, same objects but the size is different, so in that case it is able to identify both objects properly. So this was the whole thing. And yeah, for the last 10 epochs it basically was run for 448 cross 448 values. In this here, what happened is, in classification, once the classification was over, right, they removed the last convolution layer. So the last convolution layer was removed. Next what they did is they added 3 cross 3 and 1 cross 1 values. So they added two convolutions, 3 cross 3 and 1 cross 1, after removing the last convolution layer features, because since we have to be doing classification, so classification gives out the feature values, we remove the last layer of that so that we get a more refined kind of stable strong framework data set, and data set, I'm saying strong framework convolution model. And once you have that, what they did is they added a 3 cross 3 and 1 cross 1 convolution layer after this, all right. So this is an interesting thing that they added in YOLO v2. I am sorry if all the slides are kind of misplaced here, I thought of something else and then something else happened. So basically what was happening was, if you remember, in YOLO v1, the last value, that means the last convolution layer, only that was responsible for reshaping the values, and once you reshape you get the 7 cross 7 cross 30, right? So this was the whole thing basically. In YOLO v2 what they did is, to make sure of the different sizes and get different values and features, what they did is basically they took this last value, or the value for prediction of the object detection, from 3 different layers. So 3 different layers. By the way, let me mention you, these layers, they are also known as 3 different scales, so they are on different scales. And this helped in what? So basically now it will be predicting values from 3 different scales. In YOLO v1 it was only from the final layer, so they changed that in YOLO v2 and they added 3 different scales. So this multi-scale thing helped us choose basically what values or what dimensions we needed and the objects. So this helped in basically helping us also with the small object problem, since sometimes the objects are very small, so you might get the feature but they might not be used for object detection. In this case, this helped into putting things into perspective, because we were getting values from three different scales. Okay, now once that is happened, the next thing is basically they added multi-scale training. So right now, if you will see any of the algorithm or anything like that, they have a particular size, right? So you have to have the image in that particular size, only then you can put this for training. So what they did was basically they different trained on different image sizes. So what this basically means is, first let's suppose we have 224 cross 224, right? They train this for 10 epochs. What they do is then randomly choose some other image dimension weight. Okay, so let's say I choose randomly 448 cross 448. Now since the dimension has changed, it automatically has the whole thing where the convolution layers will change also. So the convolution layer sizes, the max pooling and everything, that also changes. Although the number of filters remain the same, the size of the filters remain the same, but even then the final values, because see, even if we don't have to change the values from the convolution, right, at the end we have to flatten this out to form a fully connected layer. So in that case, the number of neurons or in the fully connected layer here, this basically needs to keep changing. So in that way, what they did was they randomly select a particular size of the image and input dimension, and they keep changing for every 10 epochs randomly. So for 10 epochs now it will train on this, then it will again change the value, and they made the model so that it can adjust based on the input shape that has been generated. Alright, so this was basically the whole thing about YOLO v2. Even though YOLO v2 was not that great when it came to MAP, it still helped in what? It helped in increasing your FPS, frames per second. Alright, so these were some of the things with YOLO v2. So what was basically the whole thing, if we remember, if we go back and understand. So in YOLO v2 we had batch normalization, number one. Then instead of using 2 bounding boxes, this increased to 5. This 5 was basically due to the result of k-means clustering. We got 5 different clusters, hence the value is 5. Alright, then it removed GoogleNet and added darknet 19. Darknet 19 is a structure of its own. Once you have that, what they did was they classified the image, and classification was done on 224 cross 224 size for 160 epochs, and 448 cross 448 size for the next 10 epochs. Once that was classification was over, they removed the last convolution layer, added a 3 cross 3 and 1 cross 1 convolution. Okay, and what other things that they did was basically instead of using values from just the final layer, it used values from 3 different layers to get 3 different scale values. And the other thing was basically this was randomly trained on different image sizes, so the model can handle sizes of many different images of many different sizes. All right, so this was the whole thing about YOLO v2. Now let us come to something known as YOLO 9000. So YOLO 9000 basically means is, right now we are training, the whole thing that we are doing is, even in YOLO v2 it was trained for 20 objects, but 20 objects is not enough for us. We need more objects, right? There can be something else and something else, hence the name YOLO 9000. Alright, because this was trained on 9000 objects. In YOLO 9000, the main problem, first of all, my very big problem is, see, your detection data sets are smaller than your classification data sets. Because see, even in classification, if you remember, the last final layer had 1000 softmax values, right? So it can detect 1000 classes. In detection we just went till 20. So the detection datasets are smaller in size also, not just the outputs that it's giving out, but also in size. The number of images are not that much, because it is a bit difficult to get the detection dataset. It is time consuming. You have to label all the values on your own. So that is what was one problem. Secondly, uh, other thing was basically, if you remember, in classification you have a lot of classification. So even if there is, let's suppose, a dog, so in detection it might just be a dog class. In classification this can be even more further categorized to German Shepherd or Rottweiler or something else, right? So the whole point here that I'm trying to explain is basically classification is very detailed. So here it does not just have dog, it has even different divisions or different categories of dog. But in detection we do not have all such values, hence we made something which is known as a YOLO 9000. And to solve this problem, what this did was basically the YOLO team, the darknet team, what they did was basically they made this word tree to solve the value. So what word tree basically is, see, first you detect whether this is an object or not. Once you have that object, you detect it into further smaller values, and once you have those values you can detect it into even more further values. Like here you can see you have the physical object and you have animal here, so it has been detected animal, but we do not want it to be this vague, we want it to be even further classified. So in animal we have cat, dog, fish. In cat again we have Persian, we have tabby. Now can you understand what is happening? In vehicle also you have ground vehicle, water vehicle, air vehicle. In ground vehicle itself you have car and something else, something else. Even in car you can have different specifications. So word tree is basically in that format, if you will try to understand, kind of an hierarchical thing where for everything you have even more detailed values. So this helps in giving you more classification values. So the way that this is trained is basically the whole YOLO 9000 was trained on word tree. So what they did was basically first they identify if there is an object or not. Then you have, let's suppose, 20 classes, so it identifies which 20 classes it belongs to. Once you have that class, it further goes on to identify from this 20, let's suppose this has been classified as a cat, so from the cat, now which cat does it belong to, tabby or Persian or something else, right? So in that way the whole word tree was trained on this. So now there are a lot of things that is very helpful because of this. We will talk about this here. So what this basically means is, like here you can see you have a physical object. So for every value, let's suppose you have probability that this is an object, so this is equal to 0.95. okay, so the next thing I will be going is checking for probability of which class in the object. I found out it is from class animal, so because it has a probability of 0.75. Next I will go and understand which animal. So probability of dog, given it is an animal, now that gives me a probability of 0.8. And then what I'll do is, okay, the probability that it is a hunting dog, given that the object is a dog, is 0.63. fine. And the next thing that I'll be doing is probability that it is a sight hound, given hunting dog. Now this is equal to 0.63, sorry, 0.27. Now this value is very low. So in that case what I'll do is I'll keep a threshold. Let's suppose my threshold here is 0.5. Now I am just supposing this, okay, this might not be the real value. So let us suppose my threshold is 0.5. In that case what will happen is, first it will compare this. See, sight hound is very less, the probability that it is a sight hound is very less compared to 0.5, but the probability that it is a hunting dog is 0.63. So your object in that case will be detected as hunting dog. Or not dog, not animal, not physical object, it will be detected as an hunting dog. If suppose this hunting dog value was also even low, let's suppose 0.2, so in that case it will detect your object as a dog. Now can you understand this hierarchical word tree kind of thing that is happening? So that was one thing, and this was everything about YOLO 9000. So the whole thing point was basically they combined the detection plus classification data set in a word tree format, alright, and then all the classifications were basically done using this, and this was nice and all, but then what we had was YOLO v3. So in YOLO v3 what they did was basically, instead of using first of all while calculating the object score, so object score, or basically in that 7 cross 7 cross 30, if you remember, you had 4 coordinate values, right? And after 4 coordinate values you were getting 1 confidence score. Now this confidence score was changed, and this was found, this confidence score, now this was found using logistic regression. So you used logistic regression basically to find the confidence score. This was one change in YOLO v3. Okay, this is not that big a change, but there is some other change that is big. So in YOLO 9000, what they did is basically they used a word tree. In YOLO v3, what happened is they changed the word tree to independent linear regression models. Okay, independent sigmoid trainers. What that means is, see, suppose you have an object. So you have an object. So this object is, let's say this is a girl. So a girl can be labeled as a woman also, or maybe a girl. Let's forget the whole women analogy. So suppose you have a girl, the object is a girl, so this might be labeled as a girl, but at the same time this can also be labeled as a person. This is like what we did in your word tree. This can be labeled as a sight hound, it can also be labeled as a hunting dog, it can also be labeled as a dog, because all these 3 values are correct values, right? So to solve this problem, what they did is basically, this was not possible when you were doing the word tree, because in word tree you are getting the hunting dog or you are getting the dog, not both of these combined at the same time. So what they did was, each class, now when you get a feature map, right, when you are getting some value here, they will be passed through all these different sigmoid layers, sigmoid, or better you can call it a logistic regression layer, to find out if it belongs to that particular class or not. So let's suppose this here, this logistic regression now belongs to woman. So the first thing that it will do is it will go and classify whether this is a woman or not. So it gave us 0.7% value that this is a woman. Okay, the next thing, this will go again and go for now the logistic regression classifier for a person. If that is a woman, it is also a person, so it gave us 0.75% that it is a person also. But for cat it will give 0.01 value. So you can understand. So what this does is basically, see, if you are a person, sorry, if you are, let's say, a woman, in that case you can also be a person. If you are a cat, at the same time you can also be a Persian cat. So this distinction was important, hence what they did was they used independent classifiers. Then they made some changes in darknet. So this is the darknet structure. By the way, this is not darknet 19. The whole darknet 19 was kind of this structure. This is darknet 53. So instead of using darknet 19, they shifted to darknet 53 in YOLO v3. And what they did was basically they made some structures kind of identical things. And these structures were then later used to identify the features. So if you remember when I talked about it, even in AlexNet and everything, they had some structure. They had 2 convolution followed by 1 max pooling. So each of this structure was responsible to give me some particular feature. So they had divided darknet in such a format that this can be used as a feature extractor also. Alright. So that is it. I hope you enjoyed the video. And just a very quick recap is basically in YOLO v3, the changes that they made was, instead of word tree, now they will have independent logistic regressions for identifying the confidence value that it belongs, it is an object or not. You use logistic regression instead of the basic thing. In YOLO v3 they changed the layer, the main architecture to darknet 53. When we were talking about darknet here in YOLO v2 and everything, that was darknet 19. This here is darknet 53. And finally they had also this feature in YOLO v3, by the way. So they had these 3 different scale values. Alright, so that is it. I hope you enjoyed the video. Now that we have completed all of the object detection architectures, right? So object detection is over. So now our next task can be to go and understand how this can be done using practical cases. Alright, so we will be understanding about the code of this and how this is done. I hope you enjoyed the video and keep learning.